Hey everyone, in this exercise, I will look at the various decoding strategies while generating text with GPT-2. So, what is decoding strategy? In language-based generation task, we typically build a model which outputs a set of probabilities to an array where each value in that array represent the probability of a specific word or specific token to be generated. And the job of the decoding strategy is to select the token from that array of probabilities. Now, an obvious answer is you can think of that when you have a set of probabilities in an array, you just choose the token with the highest probability. But it is not always as simple as that, because in that case, if you just choose always the token with the highest probability, you may face many problems. For example, your generated text will be very repetitive and boring. So there are quite a few strategy implemented in this space to generate the text with the correct amount of probability or with the correct strategy, and that's what we'll look into in this video. And a good decoding strategy that transforms the model's output probabilities into discrete tokens can improve the text quality significantly. Hence, finding the best decoding strategy requires some experimentation and a subjective evaluation of the generated text as well. And these are the main decoding strategies that we are going to discuss in this video, which are greedy search, beam search, and random sampling. So within the random sampling family, we have top P and also top K. Yeah, so this will include both top K and as well as top P. Right. And all of these three functionalities can be used for autoregressive language generation models. In short, autoregressive language generation is based on the assumption that the probability distribution of a word sequence can be decomposed into the product of conditional next word distribution. And this is the mathematical representation of these. If you search for these autoregressive models, you will get many blogs explaining it pretty well. So I'm not spending more time. Just know that the very well-known GPT-2 and GPT-3 falls under these architecture. All right, with that, let's start with the actual code. Obviously, if you do not have transformer installed already, you need to run this command, pip install transformer, to install your transformer in your machine. I already have this, so I don't need to run that. And importing my torch and auto tokenizer and auto model for casual LM, the regular imports. Device will be Qdom. And the model that I'm going to use for this video is GPT-2 Medium. This is obviously from Hugging Face. And there's another model, GPT-2 XL, but that's a relatively larger model, and it takes a much longer time to work with that model, and that's why I chose GPT-2 Medium. But for your more serious case, you definitely should use GPT-2 XL, because that's, although that's larger, that's definitely a better model. All right, the first one is greedy search decoding strategy. So here, this is a simplest decoding method, and which is to get the discrete tokens from a model's continuous output by greedily selecting the token with the highest probability at each time step. And this is a mathematical representation where p represent the probability and yt here, this t here represent the timestamp. So greedy search decoding is relatively rarely used for text generation tasks that requires diversity. It can be useful for producing short sequence like arithmetic, where a deterministic and factually correct output is very important. But then where you need diversity or a little bit of creativeness in the generated text, then greedy search decoding is definitely not your choice. All right, in below right now I am going to implement greedy search kind of from scratch. And what I'm going to do that at each time step we pick out the model's logits for the last token in the prompt and wrap them with a softmax to get a probability distribution. And after that we will pick the next token with the highest probability and add it to the output sequence and run this process again and again. I'm just importing pandas here and also defining time steps and choices per step. And here I'm going to define a method for implementing the greedy search. And the reason that I'm doing it from scratch is to understand the working of the greedy search from fundamentally, that is what's happening under the hood. But in our GPT's model.generate method, we already have a parameter where we can directly mention whether I want greedy search or beam search or some kind of random sampling. So you do not really have to do it from scratch while you are actually working and implementing on a real data set. But here the motivation or the target is to understand everything from scratch. So let's proceed. Get next token greedy. It will take input text and also input IDs. Okay, so here I am going to run the decoding for 8 time steps. So first I'm going to declare a context manager with torch.noGrad because I do not need the grad here. These iterations dict that will contain the whole input tokens and also the predicted tokens in a dict format, and ultimately at the end of this function I'm going to convert this to a pandas data frame so we can print and present it in properly in a tabular form. So that's the purpose of these iterations. So iterations, now I'm going to include a key called input because that will hold the continuously updated input token. And then I'm also going to add, so input is like one column in the final data frame that I will have. And also I'm going to have choice 1, choice 2, choice 3, 4 and choice 5 as different columns, because here we are doing choices per step equal to 5. So I will have 5 columns for 5 choices with decreasing probabilities of the predicted token. So yeah, once we complete this function, it will make sense. Yeah, input will be my I'm just decoding from the tokenizer, and this tokenizer we have already defined it over here. And then if you print this, let's print it. Actually, no need to print because I'm just going to take output.logits. But first, I'm going to define my output. And then then I'm going to get output.logits like this. From that, I need to select the logits of the first batch and the last token. So that I'm going to do by selecting the first batch for the first dimension, the last token, and the last dimension also will be everything. Yeah, so that will be held in a variable called next logits. Okay, so this next token logits, it is just a one-dimensional array. Remember these output.logits, this is a three-dimensional array. But next token logits is a one-dimensional array. So if we print these next token logits, so you will get a tensor something like this. So let's move on. Now apply, this is just a logit, so I need to apply softmax to get the actual probabilities. Okay, now I need to apply sorting. So I need to get the indexes of the sorted array from these probabilities array. So let's do torch.arcsort to that class next. Descending and hold these in a variable called sorted indices of next token probability. Okay. And again, these sorted indices of next token probat, this variable is just a one-dimensional tensor, something like this. It just holds all the indices in this variable. Okay, next I need to run a loop because I have 5 choices per step. Here is 5, so I need to run a loop over these 5 choices, so to produce just 5 predicted tokens for each of the prediction. and that's token index sorted. And then I need the actual token probability. And actual token probability I can obtain from next token probability variable. All right. And now create a string with decoded text and corresponding probability. So this string will be the um, actual element value in my final data frame. So let's quickly see what I wanted to achieve through this function. I think I should have shown it earlier. That would make sense at what I'm doing with this function. And this is the output that I'm trying to achieve with this function. So ultimately at the end of this function, when I run it on an input text, it will produce this data frame where each of these choices are the next token predicted choices, and we can see that these values in the cells, they represent the actual token that has been predicted and also the corresponding probability. So at the very first one, choice 1, that is, will be with the highest probability, then choice 2 will be the next best probability, choice 3 is the next best probability, and so on. And this is the input. So for example, the first input is Bitcoin will be, then the next token predicted is the. So that means because this is the highest probability, and under the greedy search we take the highest probability token predicted as the as my choice. So my next input will be Bitcoin will be, then I append this previous predicted the. And similarly my input will go on increasing because I'm adding with the previous input the highest probability prediction. And so in this line I'm going to define a string which will have the actual predicted token and also the corresponding probability as a percentage. And that's going to be a tuple. So this will be decode. Yes. So to the decode I have to pass the token index sorted because that's a decoded predicted token. And next one will be the percentage of the probability. .2f. Now update the iteration. Plus IBX plus 1. With that I'm out of the loop. So now I need to append the predicted next token to input. Iteration. Finally return from the whole function pandas data frame. Now time to execute this function, but before that I need to define my input text, which in this case I am just choosing this particular phrase, Bitcoin will be. And so input ID will be the tokenized form of this input text. So I need to make use of the tokenizer. Input text. Module torch has no attribute arg. Oh yeah, this is arg sort. Where did I use that? Here. And just noted that I forgot another thing to add. Because in the final data frame that is in here, which is output, I need to update these input. That is, the input will continually be updated with the previous best prediction. That means what I need to do is create concatenated input IDs. That's what I have to do. And why concatenated? Because it will be concatenated with the previous highest probability token. And I get the previous one by from this array sorted indices of next token proba. This one sorted indices of next token proba. From there I take none, 0, and also none across deal of -1. Okay, now all looks good. Just run this cell. Yes, so that's my data frame, and this is what I wanted to show, the greedy search algorithm from scratch. So we can see that the absolute final sentence will be Bitcoin will be the first cryptocurrency to be, and check our initial input was Bitcoin will be. Then I have all the choices, and the highest probability choice is this choice 1, so I add the, so the next input becomes Bitcoin will be the. Similarly, my second output or the second prediction takes the previous input plus the highest probability output or highest probability token prediction, which is first, so I add first. And then my next highest probability is cryptocurrency, so I add cryptocurrency and I get this. Similarly, I go on down and I just take the choice 1 and append it with the previous input, and finally I get this sentence. So that was implementing this greedy search from scratch with this function. And now I'm going to check if I do the same greedy search implementation by taking the help of the inbuilt functionality of Hugging Face. So my Input IDs will remain the same, which is tokenizer input text return tensor equal to pt. I take the input IDs, and now the important part, output here will be model.generate. This is the method which will give me the predictions, the generated predictions. So to that, the first argument is input IDs. Max new tokens, that will be my time steps. And what are my time steps? We already defined, that's 8. And another one I want to pass is do sample false. You can definitely check their official documentation to make sense of all these parameters. And I'm going to print tokenizer dot decode. What I'm doing, decode output. From output I take the first element. Okay, and when I ran this is my final output. Bitcoin will be the first cryptocurrency to be listed on the. Now look at my from scratch implementation result and the inbuilt Hugging Face implementation result. They are almost the same. Of course, my from scratch we ended it here, and up to this word or this token, each one pretty much matched. So Bitcoin will be, this was my absolute original input, and then this token matched the first cryptocurrency to be, and I also have the first cryptocurrency to be in my own implementation. Okay, so that was for showing the greedy search algorithm, how it works. And now I'm going to move on to beam search. Actually, before moving to beam search, I just want to define few more things, because we have to use it quite a few times in this exercise, which is I just want to define lengthier input text and generate the prediction from that input text. And then we are going to use the same input text through beam search, and then for top K sampling, top P sampling, and so on. So my input text, let me take it from a website. So this is an input text I took, and it reads, in a previous era of data engineering, data team structure was very much centralized, with data engineers and tech savvy analysts serving as librarians of the data for the entire company. Data governance was a siloed role, and data engineers became the de facto gatekeepers of data trust, whether or not they liked it. Okay, this is my input text, and based on this, I'm going to generate my generated text from GPT-2. And just like previously, we do the basic generation with our tokenizer. And for that, I'm going to define max length equal to 128, and otherwise I can just copy from here, because it is going to remain the same. So I'm tokenizing the input text, return tensor pt, taking the input IDs and moving it to the device, and then I'm outputting, that is a generated text will be model.generate input IDs max new tokens equal to time step. Okay, in this case, not, I'm going to delete only this parameter because I have something else. Max length will be max, because I'm defining a max length of 128 here. And do sample remains false. Let's run this cell. Okay, now it's generating and it is a lengthier text, so it is taking a little bit more time. Okay, so yeah, so this is my generated text. And if you read it, it says the generated part is here. But as the data industry has grown, so has the need for data governance. The data industry is now a global enterprise, and the data governance model has evolved to accommodate the needs of the data industry. Data governance is a complex topic, and it is not. Okay, so this is my generated part, and this was generated based on the greedy search. And now I'm going to do beam search. So the major drawback of the greedy search was that it misses high probability words hidden behind a low probability word. And thankfully, we have this beam search to alleviate this problem. So with beam search, at each time step, it generates all possible tokens in the vocabulary list. Then it will choose the top B candidates that have the most probability. Those B candidates will move to the next time step, and the process repeats. So instead of decoding the token with the highest probability at each step, beam search keeps track of the top B most probable next tokens, where B is referred to as the number of beams or partial hypothesis. The next set of beams are chosen by considering all possible next token extensions of the existing set and selecting the B most likely extension. In summary, whereas greedy decoding and random sampling calculates the best option based on the very next word or next token only, beam search checks for multiple word or multiple tokens into the future and assesses the quality of all of these tokens combined. However, because we are now back to ranking sequences and selecting the most probable sequence again, beam search can cause our text generation to again degrade into repetitive sequences. So with beam search as well, we can get repetitive generated text. But there's more solution on that as well. We'll look into that in a second. And now for the implementation, looking into the under the hood working of beam search. Note that transformer models return the unnormalized logits for the next token given the input tokens. So we first need to normalize the logits to create a probability distribution over the whole vocabulary for each token in the sequence. And we then need to select only the token probabilities that are present in the sequence. So let's write some function to do this. So this function that I'm writing will get me the log probabilities from logits for a single token. So I'm being explicit with my method name nomenclature here. Get log probs logits only token. Log probability will be equal to, I'm going to use f.log softmax. So this is not softmax, this is just, I mean, this is pretty much softmax, but this is, instead of being a regular softmax, I'm going to use log softmax because that's what is needed under the beam search techniques. And here I need to use torch.gather log p. Next argument is 2 label double EZA 2. Oh, LABELS and return me the log p label. Okay. So the above gives us the log probability for a single token. So to get the total log probability of a sequence, we just need to sum the log probabilities for each token. And also a quick word on these log softmax function. So the log softmax is simply a logarithm of a softmax function. The use of log probabilities means representing probabilities on a logarithmic scale instead of the standard 0-1 interval. And the use of log probabilities improve numerical stability when the probabilities are very small because of the way in which it's computed. So taking the product of a high number of probabilities is often faster if they are represented in log form. And that's pretty much the reason of using log softmax. And about the storage.gather, this function creates a new tensor from the input tensor by taking the values from each row along the input dimension. And in here our input dimension is 2, that is dim equal to 2. And now I need to write the next function for the sequence log probabilities. And here if I these output, I need to take the output.logits for the next steps. And if we print these output.logits here, that is if I do something like output.logits.shape, then the result that I will get is it's a tensor of size 1 by 128 by 50257. So the first dimension here is a batch size. The next dimension is a sequence length, or the which we have defined here to be 128. Remember, max length 128. And the last one is the embedding vector size. So that's the total number of tokens in GPT-2 model that we are using here. Okay, so this was just for showing log probs is going to be equal to that method. The first one is the logits. So output logits. I need to take everything from the first dimension, then from the second dimension everything but the last element, and for the third dimension everything again. And the second argument of this method, get log probability from logits for single token, is the labels. So just pass labels. Okay. Note that in this formulation, we ignored the log probabilities of the input sequence because they are not generated by the model. We can also see that it is important to align the logits and the labels. Since the model predicts the next token, we do not get a logit for the first label, and we don't need the last logit because we do not have a ground truth token for the last logits. And that's why this adjustment over here. Now I just need to sum over the tensor. Sequence log probe. All right. Now let's use this function to first calculate the sequence log probability of the greedy decoder on our previous input text. So we already have this input text defined, and we also defined the output by using model.generate. Actually, this output is representing the greedy search algorithm. So let's just define it, output greedy. Okay, and this one as well. Okay, let it run that cell. By the time, let me write few codes here. Sequence log probability. So I'm going to use this method, and it takes a model which we already have defined, and the labels will be my output greedy, and input len, which is len of input IDs 0. What I'm going to do, print tokenizer.decode output greedy, also print new line character, log p.2f. Yeah, let's run this. Sequence log okay, let me correct it. Oh, because I did not run these two cells. And now after running this, I get this output, and look at the log probability of 90.66, which is not too good. But now let's compare this to a sequence that is generated with beam search, because then we can actually make sense of the differences. So let's proceed. So previously I already had this output greedy, and now I need to do the same for output beam. And both output greedy and output beam are like a two-dimensional tensor. If you just print this output greedy, you get a single two-dimensional tensor. And I take the 0th element because I'm just 0th element because I'm just practically flattening it, because it's just you can see two square brackets here. Anyway, so my output beam also need to be of the same form. Let's start the coding for that. Output beam, and look at what I need to do to generate my output beam. Just pass one particular parameter into model.generate. So first argument remains input IDs, max length remain. So this is max length. Yeah, so this is the important parameter in model.generate. So only change you have to make is just pass this numBeams argument to produce your beam search output. That is all. And if you don't pass this, then by default it will produce the greedy search result. And finally, do sample, which remains false. Log p will be equal sequence log prob. And 0. And the last two I can just copy from here. It's taking a couple of seconds to run. Okay, so it ran pretty quickly, and now I get log probability of minus 27.22, and we can already see that we get a better log probability. That is this number, the higher it is better with our beam search than we did simply with greedy search. So with greedy search we got much lower, that is 90.66, and now with beam search I got much better, minus 27.22. But looking at the generated text here, we can see there are some repetitions. So this above result of minus 27.22 as a log probability, although it is not too bad, we have managed to stop the repetition to some extent, but we have not completely got rid of the repetition. So one way to address this repetition issue is to impose an n-gram penalty with the no repeat n-gram size parameter that tracks which n-gram have been seen and sets the next token probability to 0 if it would produce a previously seen n-grams. And for that, again, all we need to do is just change a particular parameter. So I'm just going to copy this entire thing first, paste it here, and I need to pass here no repeat n-gram size. I'm passing it to be 2. Okay, and now let's run this again. Alright, and now I get a log probability of minus 69.73, which is not as good as minus 27.22, but still much better than minus 90.66. So the above result, actually this result actually is not too bad. We have managed to stop the repetition, and we can see that that despite producing a lower score, the text remains coherent. Beam search with n-gram penalty is a good way to find a trade-off between focusing on high probability tokens with beam search while reducing repetitions with n-gram penalty. And it's commonly used in applications such as summarization or machine translation, where factual correctness is important. When factual correctness is less important, then the diversity of generated, when factual correctness is less important than the diversity of generated output or generated text. For instance, in open domain chit chat or story generation, another alternative to reduce repetition while improving diversity is to use random sampling, and that's what we are going to look at next. And now random sampling with temperature. So sampling based family of techniques aims at increasing the diversity of the output and avoiding repetitions by introducing stochastic decisions during the generation process. Here, the underlying basic principle is that we can utilize the probability of each token from the softmax function to generate the next token. The simplest sampling method is to randomly sample from the probability distribution of the model's outputs over the full vocabulary at each timestamp. And here is a mathematical expression, and this is actually the formula for random sampling with temperature. The temperature is denoted by these letter T, and the temperature is used to increase the probability of probable tokens while reducing the one that is not. And by tuning this temperature variable T, we can control the shape of the probability distribution. When T is less than 1, the distribution becomes peaked around the origin and the rare tokens are suppressed. On the other hand, when T is greater than 1, the distribution flattens out and each token becomes equally likely. And now I'm going to see the effect of this temperature variable on the token probability. So I'm going to define a couple of functions and then plot a basic plots where I'm going to show different plots for different values of the temperature variable, starting from 0.5 to 1 and then 2. So first import this is a customized softmax actually, where I have a T variable representing the temperature. Logits divided by T, and what I'm going to return is divided by sum. That's all. Now define some random logits. Sorted logits, np.sort logits, and from that I reverse that one. So for reversing, I'm going to use slice and -1. Okay, and my x variable just will be np dot and now the plotting. And I'm going to plot a loop over three variables, three values of the variable T, which is 0.5, 1.0, sorted logits scheme. Labels will be, label, it's a string which will have T equal to the actual value of the T. Dot y label is just the probabilities. Yes, so that's my plot, and we can see there are three values of T, and that's how the sorted token probabilities will evolve over the values. And now to see how we use temperature to influence the generated text, let's sample with t equal to 2 by setting the temperature parameter in the generate model.generate method. So I go back to my the original method of model.generate. Input IDS, max length equal to max. Output temp, yeah. And looking at these output, we can see that the output is clearly doesn't it's all producing some garbage words, and that's because we used a high temperature over here. And the high temperature, what it's doing is that it is accentuating the rare tokens, and thereby we have caused the model to create strange grammar and quite a few made up words. And now let's see what happens if we cool down this temperature. And so I ran the very much same 2 lines again, only changing temperature equal to 0.5, and this is the output that I get, and this is my generated text. And we can obviously see that this text is significantly more sensible output. And the main lesson we can draw from temperature is that it allows us to control the quality of the samples, but there's always a trade-off between coherence, that is low temperature, and diversity, that is high temperature, that one has to tune to the use case at hand. And another way to adjust the trade-off between coherence and diversity is to truncate the distribution of the vocabulary. This allows us to adjust the diversity freely with the temperature, but in a more limited range that excludes words that would be too strange in the context, that is low probability words. And there are 2 main ways to do this, which are top K and top P sampling. Let's do them. So top K and the top P sampling are 2 popular alternatives or extension to use temperature. In both cases, the basic idea is to restrict the number of possible tokens we can sample from at each time step. The idea behind top K sampling is to avoid the low probability choices by only sampling from the top K tokens with the highest probability. This puts a fixed cut on the long tail of the distribution and ensures that we only sample from likely choices. So in top K sampling, the K most likely next words are filtered, and then the probability mass is redistributed among only those top K words. So let's take a look at this image over here representing the top K probability techniques, architecture, and how the probability mass is redistributed. So having K equal to 6, in both sampling steps, we limit our sampling pool to 6 words, while the 6 most likely words defined by this image here encompass only 2/3 of the whole probability mass in the first step. It includes almost all of the probability mass in the second step. And that's exactly what we mean, that in top K architecture, the probability mass is redistributed among only the top K probability words. Now let's just implement it with model.generate. And again, I only need to change a single parameter in my model.generate to implement it, and that's this top K parameter. So here in this code, I'm just using a top K equal to 50, and let's run this. And this is the output. We can see that the repetition is much lower in this case because because these kind of algorithms specifically deal with not to have repetitions. And now the next and equivalent, almost close concept to top K is top P, or nuclear sampling. So here what happens is that so this is a pictorial representation of top P probabilities. Now we are no more looking at top K but top P. So instead of sampling only from the most likely K words, the top P sampling chooses from the smallest possible set of words whose cumulative probability exceeds the probability P. The probability mass is then redistributed among this set of words. This way, the size of the set of words, also known as the number of words in the set, can dynamically increase and decrease according to the next word's probability distribution. And yeah, so that's the fundamental concept here. So again, to understand how top P works, let's say we set the value, that is a P value, to be 95%. We then order all tokens in descending order by probability and add one token after another from the top of the list until the sum of the probabilities of the selected token is 95%. Thereby, we are choosing the top words whose cumulative probability is 95%, and we focus our attention only on those words, and that's how top P works. And to implement it, probably you have already assumed, we only need to change one parameter, which is here top P, and there you specify the probability that you want, and here I'm specifying 0.90. That means it will choose only those words whose cumulative probability is 0.90, and only those words will be concerned. So just run this cell, and here's the output that I get from my top P decoding strategy. Alright, so those pretty much were the discussion points in this video, and if you are thinking which decoding method is the best, well, unfortunately, just like many machine learning algorithms, there is no universally best decoding method. Which approach is best will depend on the nature of the task you are generating text for. If you want your model to perform a precise task like arithmetic or providing an answer to a specific question, then you should lower the temperature or use deterministic methods like greedy search in combination with beam search to guarantee getting the most likely answer or most accurate answer. But if you want your model to generate longer text and even be a bit creative, then you should switch to sampling methods and increase the temperature, or use a mix of top K and top P sampling. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So, see you in the next one. Thank you very much for watching.